Hello student, in this lecture we will continue with our log-based protocol. We have already seen about the log-based protocol. So this locking protocol divides the transaction execution phase into a three phase. So here we have given a figure of the log-based protocol. Here we have one transaction that is started from T begin, ended at T end, and here the arrow indicates the timeline. So when transactions start executing, it creates a data item on which they need locks. Suppose one query want to execute on our database and it requires 3 number of records. So this is what the number 3 number of records, the list of a data item on which that particular query want to process, and request the system for all the lock it need, and then it will request that I am going to perform some operation on these 3 record, so it require lock so it can process further on the same number data. So here we have lock acquisition phase that is started at the timeline T begin, and once when the transaction acquire all the locks and no other lock is required, transaction keep executing its operation. So when all the data item that is required by that particular query, when it is available, then that particular query get the lock, or system provide the lock for that particular query, and it start its execution. So this is the time of execution. This is from T begin to T end. So this is the execution time. As soon as the transaction release its first lock, the third phase start. Suppose here it require 3 data item, and after the completion of the work, one by one it start to release that lock. So that after the third phase start, in this phase a transaction cannot demand for any other lock but only release the acquired lock. So from this stage, when the transaction execution completed, it cannot get any other lock, or system does not provide any additional lock, because here in this phase that particular transaction just have to release the acquire the lock that is provided by the system. So this is a two phase locking protocol. Now there are 2 phases of the 2-phase locking protocol. First stage is the growing phase. So in this phase, transaction obtain only locks, but it cannot release any kind of the lock that is already occupied. When the transaction takes the final lock, is called the lock point. So when it is get each and every lock that is required by that particular query or a transaction, that particular thing is known as a lock point. And in the shrinking phase, so in this shrinking phase the transaction can release the lock, but it cannot obtain any kind of the lock. So in the shrinking phase, the transaction just have to release the lock that is acquired by that particular transaction. The transaction enter the shrinking phase as soon as it release the first lock after crossing the lock point. So here we have a given figure, growing phase. So in growing phase, that particular transaction acquire the lock on the particular data item, and this is the time of the execution. And if all the execution is successfully completed, then we can say it is into the shrinking phase. And in shrinking phase, that particular transaction have to release the lock one by one. But remember one thing, in shrinking phase that particular transaction cannot obtain any other lock, or it cannot or system cannot provide any other lock for that particular transaction. Now we have a strict 2-phase locking protocol. In this protocol, a transaction may release all the share lock after the lock point has been reached. So remember, in the strict two-phase locking protocol, once the required lock is of the category of share lock, so the strict two-phase locking protocol release all the share lock after the lock point has been reached, but it cannot reach any kind of the exclusive lock until the transaction commit or abort. And we know the share lock is generally provided on the data item read operation only. Okay, so it ensures that if data is being modified by one transaction, then other transaction cannot read it until the first transaction commit. So this protocol solve the dirty read problem. So strict two-phase locking protocol is used to solve the problem of the dirty read problem that we have already seen in the previous lecture. Now we have another protocol, this is rigorous two-phase locking protocol. In this protocol, a transaction is not allowed to release any lock, either it is share or exclusive. As we have seen in the previous protocol, it release all the share lock, but rigorous two-phase locking protocol not release any kind of a lock. It may be either of the category of share lock or exclusive until it's commit. So this means that until the transaction commits, other transaction cannot acquire even a share lock on the data item on which the uncommitted transaction has a share lock. We have another protocol, timestamp based protocol. As the name suggests, it is deal with the time, because timestamp based protocol is there. This protocol can either use the system time or a logical counter to be used as a timestamp, because timestamp protocol is purely based on the timestamp. It is logically provided by your database management system, or it may be use the system time of your operating system. So every transaction has a timestamp associated with it, and ordering is determined by the age of the transaction. Now we can identify the age of transaction by its time, because here we have to find out the age, and age is nothing but a transaction time at which point it started. A transaction T1, suppose created at the 0002 clock time, would be older than all other transaction which comes after it. So suppose one another transaction, that is namely T2, is created at the 0005 or 6 clock time, that means it is a newer, and our T1 transaction that is created at a 0002 clock time, it is older. So for example, any transaction T2 entering the system at the time of 0004 is a 2 seconds younger than the transaction T1, because T1 is already started on 0002 time, and the priority is given to the older one. So T1 transaction get the higher priority with compared to the T2 transaction, because it is entered into the system at the time of 0004. So in addition, every data item is given the latest read and write timestamp. So this lets the system know when last read and write operation was made on that particular data item. So this is the responsibility of the protocol system, that the conflicting pair of the task should be executed according to the timestamp value of the transaction. Timestamp of the transaction Ti is denoted by TSTI. Timestamp of the transaction Ti is what? Transaction, and its timestamp is denoted by TS. So read time stamp of the data item X is denoted by R, that indicate the read operation, the timestamp, and this is the data item that we want to read. Write timestamp of the data item X is denoted by write operation. Here W indicate the write operation, and write operation started timestamp, and X is the data that we want to modify or write. Here we have timestamp ordering protocol. So in timestamp ordering protocol, it works as follow. If a transaction Ti issue the read operation on data item X, and if the timestamp of Ti transaction less than write timestamp of the data item X, then operation should be rejected. Or if the timestamp of the Ti transaction greater than or equal to write timestamp of the data item X, then operation should be executed. If the transaction Ti issue the write X signal or operation on the data item X, then if the timestamp of the Ti less than the read timestamp of the data item X, then operation should be rejected. Or if the timestamp of Ti transaction less than the write timestamp of the X, then operation rejected and Ti should be rollback, otherwise operation should be executed. So this is a kind of a algorithm or a working flow of the timestamp ordering protocol for to read and write a particular transaction. Now we have a new topic, deadlock. So what is deadlock? So here we have one figure. Consider the following two transactions. So here we have a T1 transaction and T2 transaction. Here suppose the T1 transaction, initially we don't have any transaction into the system, and T1 transaction want to execute. So it require a lock X on data item A and write that particular data item A. So here we don't have any transaction right now currently executing on the system, so granted for A, because there is no any other transaction is working for A. Now transaction T2 enter into the system, and here it want to lock the B data item and want to write that data item B. So again it granted for the B, because here we don't have a right now any operation or a transaction working on the data item B. But after the completion of transaction T2 for the B, again transaction T1 want to access the data item A. But here we know the transaction T1 is already working on the data item A, and here the transaction T2 also want to work with the data item A. So here the transaction T2 has to wait for the data item A, because transaction T1 is already working on the A. So here this operation of transaction T2 cannot be completed. And here check out, after some few time transaction T1 want to lock on the data item B and want to write for the B. So here operation for that particular data item B, the transaction T1 has to wait, because already the lock is occupied by transaction T2. So here the circular condition is arise, because T1 is already obtained the lock for the data item A and want to get the lock on the data item B, and for the transaction T2, the T2 already acquired the lock on the data item B and want to get the lock on data item A that is already locked by the transaction T1. So here no transaction will release the lock forever. So this is the condition known as a deadlock, because T1 never release the data item X and T2 never release the data item B, and both the transaction waiting for the other item for to complete its operation. So a deadlock is a situation in which two or more transactions are waiting for one another to give up the locks. So this is known as a deadlock. Now, how to detect a deadlock? A simple way to detect a deadlock is with the help of the wait for a graph method. So one node is created in the wait for the graph for each transaction that is currently executing. Whenever a transaction Ti is waiting to lock an item X that is currently locked by the transaction Tj, a directed edge from Ti to Tj, something like this, is created in the wait for graph. When the Tj releases the locks on the data item that is Ti was waiting for, the directed edge is dropped from the wait for graph. We have a state of the deadlock if and only if the wait for graph has the cycle. So if wait for a graph has a cycle, that means it is a deadlock condition. So then each transaction is involved in the cycle if it's said to be deadlocked. So here we have a deadlock detection. Transaction A is waiting for the transaction B and C. Here we have a transaction A that is waiting for a transaction B and transaction C. Transaction C is waiting for the transaction B. Here a transaction C is waiting for the transaction B. Now the transaction B is waiting for the transaction D. So here transaction B is waiting for the transaction D. So this wait for graph has a no cycle because we do not have any circular condition. So there is a no deadlock state. Suppose now that a transaction D is requesting an item that is held by C. So if a transaction D want to process on the data item that is already held by C, then the edge of D to C that we have drawn over here is added to the wait for graph. So it becomes something like this when we draw the arrow from D to C. So here is the figure that we have already drawn. So now this graph contains the cycle, and cycle is what? Here C is requesting for the resources of B, B is requesting for the resources of D, and D is requesting for the resource C. So B, D, C, B. So started with B transaction and ended with the B transaction. So it means that the transaction B, D, C, B, D and C are the deadlock because it has a circular condition. So no one release the lock and no one get the lock for the data item on which they want to perform. Now deadlock from the recovery. When a deadlock is detected, as we have seen in the previous lecture, as we have seen in the previous slide, because we have find a cycle, and cycle means what? Circular condition, and circular condition is the detection of the deadlock. So once we find a deadlock into the system, by the graph. So how we can recover from that deadlock? So the system must recover from the deadlock. The most common solution is to roll back one or more transaction to break the deadlock. Choosing which transaction to abort is known as a victim selection. So here we have a previous condition of the deadlock. So in this wait for a graph transaction, B, D and C are into the deadlock. In order to remove the deadlock, one or more transaction out of these three B, D and C transaction must be rollback. So either B may be a rollback, D may be a rollback, or a C may be a rollback. So we should roll back those transactions that will incur the minimum cost. So out of these three transactions, which transaction we have to roll back, which has a minimum cost? And when the deadlock is detected, the choice of which transaction to abort can be made using the following criteria. The transaction which have the fewest lock, a transaction which has a minimum locks, the transaction that has done at least work, the transaction that has done the least work, because all or a minimum work done by that particular transaction. Such kind of transaction we can abort. The transaction that is farthest from the completion. Okay, so or a transaction that require a more time to be completed its operation. So these are the thing by which we can find the victim. Now deadlock prevention. A protocols ensure that the system will never enter into the deadlock state. In previous topics we have find out the deadlock, system have entered into the deadlock and we are recovering from that deadlock. But suppose before the cycle generated for the deadlock, we can prevent before it. Okay, so in this topic we can find out the way how we can prevent the deadlock. So the protocols, they ensure that the system will never enter into the deadlock state. So some prevention strategies are there. So require that each transaction locks all its data item before it begin its execution. So suppose one transaction want need a 5 number of data. Okay, so once it start its execution, it acquire lock on all these 5 data. So it further does not require any kind of a data item to complete its execution. Impose partial ordering of all the data item and require that transaction can lock data item only in the order specified by the partial. Following schemes are use transaction timestamp for the sake of the deadlock prevention alone. Wait die scheme and non-preemptive. If an older transaction is requesting a resource which is held by the younger transaction, then the older transaction is allowed to wait for it till it is available. And if an younger transaction is requesting a resources which is held by older transaction, then younger transaction is killed. So wait and die. So O needs a resource held by Y, then O must have to wait. And if Y or a younger needs a resource is held by older, then younger should be die. Wound wait scheme, that is preemptive condition. If an older transaction is requesting a resource which is held by the younger transaction, then older transaction forces younger transaction to kill the transaction and release the resources. And if the younger transaction is requesting a resources which is held by the older transaction, then the younger transaction is allowed to wait till the older transaction will release the lock. So in the wound wait condition, if the older needs a resource held by the younger, then younger should be die, and if younger needs a resource is held by older, then y or younger must to be wait. Time out based scheme of the deadlock prevention. A transaction wait for a lock only for a specified amount of time, and after that the wait time out the transaction is rolled back, so the deadlock never occurs, and simple to implement but difficult to determine the good value of the timeout interval. So what should be the time of interval by which that transaction should be rolled out? It is very complicated, or it is very hard to implement, so it is not a proper solution, because it is a time consuming process to provide some time interval for checking out that particular transaction has completed its execution or not, to find out the deadlock. Here these are the some of the important question of this chapter that already asked into the GTM. Here we are completing this chapter. Thank you.